We are looking at physics in calculus, and it really starts with a basic position versus time graph that we should be looking at. Now, when we would look at something like this, if we have 2 points here, obviously the x values deal with seconds and the y values deal here with position, which we have here in feet. If I wanted to look at the slope that connects these 2 points, well, slope is just rise over run, change in y over the change in x, which in this case I would do 250 minus 100 for the y's and 4 minus 1 for the x's. So I would get 150 divided by 3 or 50. If I want to think about units, my units would be my y's over the x's, so feet per second. So what you just found out here is the slope on a position time graph gives you something in feet per second. That's a velocity. So think about that. The slope of a position graph gives you velocity. What if I had a velocity graph to begin with? I could do the same thing. I could find slope here, which would be, in this case, 50 minus 0 over 2 minus 6, which would give me like negative 12.5, but what would this unit be? My y's are in feet per second, and my time is in seconds, so that would be feet per second squared. So the slope of a velocity function gives you something that is an acceleration, and that's something you should be thinking about. The slope of position gives you velocity, and when we say slope here in calculus, we should be thinking the word derivative. So the derivative of a position function is a velocity function. Same way we said the slope of a velocity function gives you acceleration. That means that yes, the same thing. The derivative of velocity gives you acceleration. Well, I could even take the acceleration. I can do that and take the excuse me, derivative of that. Well, that gives you something we really don't talk about much. It gives you jerk, or I guess you could say it gives you boxing as a result. So derivatives of position give you velocity. Derivative of velocity gives you acceleration. That's the important thing to take away. Now, the other thing we can look at is average velocity versus instantaneous velocity. Average, when we say average, we need to think like over some period of time. So time has passed. It's like a change in y, change in x sort of thing. Instantaneous means at any one given time. So again, average time, like if you're thinking maybe about like going through a stop sign, that would mean, or if you're going through a speed trap, for example, would be a perfect example of it, that maybe you've gone too fast, you look over a period of time, they see how fast you were going based on how much time it took you to go a certain distance. Instantaneous would be like if I pulled out a radar gun to see how fast you were going at any one specific time. So that means an average velocity, if we go with what we did in the past, with secant lines. Instantaneous is more of a tangent line. So if I wanted to say, for example, the average velocity, I'm looking, like we said, the change in distance over the change in time. If I want instantaneous, that means I should be looking at a specific point, finding the derivative, and we can do a derivative function to find a velocity function. Same thing with acceleration. Average acceleration is the change in velocity over time, whereas an instantaneous acceleration is the derivative of velocity, or in that case, the double second derivative of displacement of your position function. So, how we're going to use this. Here's a problem. Let f of x equals 3x cubed minus 5x squared minus 8x plus 1 be the position function for some particle. We want to first find velocity and acceleration functions. Well, let's start with finding velocity. Velocity, we just said on the last page, is the derivative of the position function. So our position function was given here. We just take the derivative to get the velocity function. So the derivative with our power rule, 9x squared minus 10x minus 8. That is your velocity function. Same way I can find the acceleration function because it is just the derivative of velocity. So I'm just going to take the derivative of this guy, getting 18x minus 10, and that tells you your acceleration function now. For part B, what is the average velocity of a particle? Okay, when we say average velocity, so velocity average, we always want to think one step above. So the change in distance over the change in time. So like meters per second, feet per hour, whatever it ends up being. So I'm going to look at the change in time first. I'm going from 1 to 3 or from 3 to 1. Doesn't matter which way you set it up. Whatever I put here on the bottom, because this is my change in time, I'm going to do the same thing but with my function, my change in distance up top. So f of 3 and f of 1. This should be how I set it up every time. Okay, so I'm just going to plug into my equation now to find out what those values are. So when I plug into a calculator, when I plug in 3 into this function, I should get For this part, I should get 13. And when I plug in 1, I should get -9. So 13 minus -9 over 3 minus 1. So my top becomes 22, my bottom becomes 2, which means my answer here is 11. And whatever my units are, let's just say they were meters in seconds. So velocity would be something in meters per second. Now, if they want instantaneous velocity, that means I am just plugging in the point, velocity at 3 and the velocity at 1. And I just plug that straight into my velocity function, which I found here in part 2. So I just plug that into my calculator. When I plug in 1, I should get an answer of -9. When I plug in 3, I should get an answer of 43. And both of these should be in, if it's velocity again, meters per second for both of this. And now let's take a look. This should make sense. The average velocity should vary, it should likely be between what the instantaneous velocities are at the endpoint. So those numbers should all make a lot of sense. So here's another example. I want to have you pause the video at this point. When you come back and see if you're ready, see if you can get all these answers correct. Alright, so what we're looking at here, we have a velocity function. Well, we were given position, we need to find velocity and acceleration. Velocity is the derivative of position, so I take the derivative of what we were given. So that's 8x cubed minus 2x plus 3. And then to find the acceleration function, I take the derivative of velocity. So I would have 24x squared minus 2. Okay, part B, they want average acceleration. Take a look at that. The acceleration average. That means it should be one position up, the change of velocity over the change in time. So what I should be looking at, first of all, my change in time is from 5 to 2. That means up here I should be looking at velocity at 5 and velocity at 2. And I need to now find what these answers should be. So when I plug in 5 into this velocity function, I should be getting 993. When I plug in 2 into the velocity function, I get 63 over 5 minus 2. So I should have 930 divided by 3, so I should get 310. And again, whatever my units are, let's say again it was in meters per second, but it's average acceleration. That means meters per second squared is my unit. Now last part, find the instantaneous velocity at each of these points at 5 and 2. So that means I should look for v of 5 and v of 2. Well, guess what? We already found those when we did it up here, finding the average acceleration. So when I plugged in 5, I had 993, and when I plugged in 2, I had 63. And this is velocity, so that's why we're in meters per second. So there you have your physics as it relates to calculus. And I'm almost going to guarantee that you should see some physics problems pop up on your Calc AP test.